cutter from Northumbria University, K parameters, temperature and target distance, and finally Katarzyna Snajdek, from Łódź University of Technology of Poland. She will talk about monitoring growth. So I can try to share my screen.
Yes, if everybody, whether you're presenting or attending, could try to put your full name into...
Yes, please.
So that we can have a look at attendance afterwards. That's one of the cost requirements. So if you're trying to change your name, it's the 3 buttons in the top right-hand corner of your screen, of your video or your section. So that would be great. Thank you.
Okay, do you want to say anything else? Because I started like this, Nicole.
Other than that, just welcome to everybody. Thank you to all the speakers for being here. Thank you to all of the participants, and hopefully it will be an interesting session for everybody. Yes, so we'll have a bit of a break after the first 5 speakers, and then have the last 4 before questions and discussion. Prabish, are you ready to take it away?
Yeah, sure. Okay. Thank you, Nicole and Elisa. Can you hear me? It's okay, right?
Yes, that's great.
Yes,
okay.
yes.
Yeah. So I'm Prabish from Northumbria University, Newcastle. Next, please. Yeah. Okay. We already most of the people are using different thin film techniques for making films. So basically, we can divide this thin film coating techniques as vacuum-based and non-vacuum based techniques. And here we are discussing mainly the vacuum-based techniques. And vacuum-based technique, most of the people are using 2 different techniques called thermal evaporation and sputtering. In a thermal evaporation, we are just heating the source material and evaporating, and it's depositing onto a colder substrate. That is the thermal evaporation. And there are a lot of limitations for this thermal evaporation. So that's why we went to sputtering technique to avoid the problems with the thermal evaporation. In a sputtering mechanism, we are basically, it's an ejection of material from the target surface and in an atomic or molecular scale due to the momentum exchange between the incident ions and the target material. And the word sputtering came from a Latin word, and it's called sputtere, which means to spit out noisily. And you can see the timeline of technologies in the development era of sputtering techniques. And the first sputtering techniques was introduced in 1800, and in a time scale, it's in the recent years actually. Yeah. It's developed to a newly technique. And next, please. Next, Elisa. Hello. Elisa, next.
Elisa.
Yeah.
Elisa, can you move to the next slide?
Yeah.
I'm sorry, I cannot move anymore. Wait, I will try from the beginning.
I can share it as well if necessary.
Now it's going again. Okay.
So, what is sputtering? That we are going to discuss. And for a sputtering, I already said, it's a vacuum-based technique. We need a vacuum chamber. This shows the schematic diagram of a sputtering system. And in this, you can see a chamber body. That's this is a vacuum chamber, and usually we keep at a higher vacuum in the range of 10 raised to minus 6 MBAR. And we have a target source material, that is target, and a substrate, the films to be deposited. And the target material is connected to a negative voltage and substrate to a positive voltage. And usually the chamber body is grounded. And when we are supplying some sputtering gas, usually we are using argon. You can change the gas if you want for a specific reason. So generally we use the argon gas. And when we are inserting an argon gas, the energetic, actually, you can already, I said, the target is negative and substrate is positive. So the electron from the target is interacting with the argon ions, and the argon ions loses one electron, so it's get ionized. So we call it as argon ion. So the argon ion is positively charged. This positively charged argon ion attracted towards the target surface because it's a negative electron. So if it has a sufficient energy, so the argon ion will hit the target surface and eject some of the material from the target surface and deposit onto a substrate. And this interaction actually depends on the ion beam energy. And if it is less than 5 electron volt of energy, the maybe a absorption or reflection may happen, and it is the range of 5 to 10 electron volt surface damage or migration will happen. And to achieve a good sputtering, we need at least energy of 3 to 10 kilo electron volt. If it is in the range of more than 10 kilo electron volt, the ion implantation will happen, which is not good for sputtering. And next, please. And to measure the sputtering quality, we use this word called sputtering yield. Sputtering yield is the ratio between the incident ion and the ejected atoms. And this sputtering yield actually depends on the main factors such as the angle of argon ion coming to the target surface, and the amount of energy during the collision, and the weight of the ions, and the weight of the target material, and the binding energy between the atoms in the target material, and the magnetic field sensing usually for the magnetron sputtering, and the plasma gas pressure. And here you can see a graph. That means angle of incidence is depends on the sputtering yield. When we are you can see here at a pi by 2, that means at a 90 degrees of angle incidence, the sputtering yield is 0. That means when you are an argon ion coming exactly perpendicular to the target surface, it will hit the target and eject some target material. But again, another argon ion come and it will collide, and the sputtering yield will be 0. And usually we are measuring the sputtering yield in a word called sputtering rate. The sputtering rate is directly related to the sputtering yield, and there are some other factors also depend on the sputtering rate. And we use the quartz crystal to measure the sputtering rate. I think the coming slides people will discuss about the sputtering rate and all. So next, please. And there are a lot of different types of sputterings are there. Clad sputtering, ion beam sputtering, ion assisted sputtering, diode sputtering, magnetron, DC, RF, confocal, reactive, HIPMIMs, and high target utilization sputtering. There are a lot of different varieties. And I think so here we are discussing only the reactive sputtering, DC sputtering, RF sputtering, and magnetron sputtering. And we will discuss all these things in the coming slides, with the coming speakers. And I think so it's okay. If you have any questions, you can ask me in the last. Thank you.
Okay. Maybe all the questions, we can do all the question in the end. So Tom, please.
Yeah, thanks very much. So yeah, I work in John Major Group at the University of Liverpool. So I'm just going to give you a quick overview on some considerations to think about when you're either getting a new target or using different targets. So could you move on, Elisa? Yes. Yeah, that's fine. So yeah, anyone working in academia is probably familiar with these kind of small scale sputtering targets, the small circular ones. They're normally about 2 or 3 inches in diameter, and that's fine. That's kind of typical for R&D sort of development. For larger scale stuff, or where you've got a kind of precious metal or you're sputtering something in industry, it's got a bit of an issue with your target utilization. So you're generally not going to use much of your actual target for the deposition process, and a lot of it will end up being, because of this racetrack erosion profile you get from where you've got a high density of plasma, you're going to mean that you're going to get this racetrack erosion, and you typically end up using only around 20 to 30% of the actual material you use before you kind of sputter through the target and into the backing plate or the magnetron or whatever. So you can use a couple of weird different techniques to improve that utilization. You can have this rotating magnetron to kind of get nearer to 100% target utilization. But even in that case, you've still got a relatively small uniform area of deposition that you kind of be depositing onto. So these small scale R&D targets are fine for small scale stuff and for multi-layer stacks. But I think most of us are probably looking at much larger scale, or eventually to be much larger scale deposition methods, kind of talking square kilometers for PV modules if that's our application. And so for more industrial targets, you can see here an example of a rectangular target that's feasible. You can make that as big as you like in principle, but you've still got this racetrack erosion profile, so you're not actually going to end up using all that much of your target. So the last example I've got there is it's a rotating cylinder of I think it's copper there. So it's your material rotates over a magnetron, and you can make that huge, and you've got pretty much 100% target utilization there. So that's the kind of what you'd be using if you're more in industry. In terms of your actual targets and what you're going to use, you've got a bit of a choice. If you're sputtering a metal, then that's a relatively simple choice, and you're just going to have a metal target. If you want to sputter something a bit more complex, then you've generally got a bit more of a decision to make. So if you're trying to sputter something like a quaternary material or something quite complex, then you have a couple of different options. Do you go from a compound target where you have the material you want to deposit, and you essentially just mix it up and grind it up and push it into a target? Or do you deposit from a bunch of different separate targets and try and match everything up? So the compound target, you're going to need to use RF power. The possible problem with that is that you don't know how much of that target material is going to transfer onto the substrate. It's not going to be a one-to-one comparison. And then also for things like oxide and nitride target, if you're trying to deposit them, then you have a couple of different options. Do you go for a metallic target, or do you go for the kind of the oxide itself? There's kind of pros and cons to them, each of them options, in terms of, you'll hear more about hysteresis and things like that versus sputtering rate. So yeah, you kind of, when you're choosing a target, you can kind of choose whether you're going to go for that or the, for example, an oxide target. Or if you want a bit more control, you can go for something that's substoichiometric. So you kind of get the best of both worlds, in that you've got a much more stable deposition process, but you can also add or take in, for example, oxygen or nitrogen out of your film with a bit more ease. So when you're ordering a target, when you've got a new target or you're starting a new process, you want to consider the power threshold for a given material in terms of how much heat you can dissipate, whether it's going to, if you put a lot of power through, it's going to crack the target due to thermal stresses. So I would just say probably be pretty conservative when you're starting a new material. When you're working with a new target, ramp it up and down slowly to try and avoid thermal shock and kind of potential cracking of the target. Kurt Lesker have they give you quite a lot of information on their website. If you're buying either your target from them or from somewhere else, they'll give you a good idea about the kind of power densities that you can kind of work with. And so if you're working with a compound target, so if you've got an oxide or a kind of a multi component target, then they tend to be a bit more thermally and electrically insulated. And so that means you've got a kind of limitation in your process. So you're going to need to bond them into a backing plate. So normally copper is mostly used. That's got high thermal conductivity and electrical conductivity as well. But you can also, if you've got a metal target, you can just clamp it kind of directly into your system. So we end up actually using aluminium backing plates because we're a bit more worried about copper in our sputtering system. You've got to think about impurities that might introduce. So for cadmium telluride, that's a particular concern. Copper's a particular concern. So you can use different types of backing plates, and then you've got to choose how you're going to bond your target into them. Each of them will have different power thresholds and power limitations. I think indium's probably the standard, but if you've got a bit more of a tricky problem, or if you've got a particular issue in your process, then you can go for some other options. Could you move on there, Elisa? Thanks. So you've just heard a bit about the sputtering yield from the previous speaker, but essentially it's the average number of sputtered particles that you're going to get for every incident argon atom onto your target surface. If you're sputtering a lot of different targets, then you probably have some kind of intrinsic idea about you'll have a kind of feel for the sputter yield for different targets. In general, like a lot of metallic or elemental targets will have a relatively high sputter yield, and your oxide targets are going to be quite a lot lower. So that'll affect your deposition rate quite strongly. And you can see there on the bottom graph, then you're going to have a kind of energy threshold of your incoming ions from which you're not going to get any yield, and then it increases quite rapidly, and then you kind of get this plateau. So you can, in principle, you should be able to calculate the sputter yield for all of your different targets. It's relatively, sort of simple to do for metallic targets. When you've got separate elements, you can kind of get some sort of idea. There's calculations that you can do, but that requires a lot of inputs that you're not going to know exactly. And so even for metallic targets, it doesn't always match up with your experimental values. So I think someone's asked why the sputter yield doesn't start at 0. So you're going to need a certain amount of energy from your argon ions hitting the target surface. If they're kind of just sort of tickling the target surface, it's just not enough energy to release it from the surface. So below that, you're not going to get any material coming off. But as soon as you're giving the atoms on the target enough energy to break free of the surface, then you'll start getting sputtering, and then that'll increase. That increases pretty quickly from there on. So yeah, you can look at it for your different metals and different elements individually, and there's a little applet there you can use, and that kind of can give you an idea about your sputter yield, and it's probably good, at least comparatively. I think a lot of people are probably going to be using the kind of compound targets, and it doesn't do as well. When you're trying to look at that, the calculations become pretty complex pretty quickly. So really just a qualitative idea I think it gives you is best for. If you wanted to try and look at it further, there's programs like this Trim. You can try and model your process a little bit in more depth. But then in principle, if you know your sputter yield and you can measure your ion density to the target, then you should be able to know roughly how many sputtered atoms are coming off total per second. And of course, not all of them are going to make it to your substrate in the end, but that kind of gives you an idea about the total amount of material leaving your target. So if you've got a multi-component target, so you've got an oxide or a bunch of different elements within the same target to deposit a compound film, then you're probably going to have some degree of preferential sputtering. Each of them aren't going to sputter at exactly the same rate, each of your atoms from your target. So instead, initially you'll have a kind of one material being sputtered quicker than the other, but then it'll kind of reach a steady state and it'll kind of balance itself out, and then you'll reach an equilibrium. So first of all, that means your film isn't necessarily going to be the same stoichiometry as your target. It's for oxides, you're generally going to be a bit oxygen poor, so you often need to add in a bit of extra oxygen into your ambient. But also it means it's probably a good idea to do some sort of pre-sputtering of your target surface before you start your main deposition. So if you just leave the shutter closed on your target, put the power through, clean the surface, you'll reach an equilibrium, and then you can start opening and do your main deposition, and that will just give you a bit more reproducible processes. So could you go to the next slide, Lisa?
Okay, Tom, you should run a little bit more because we are out of time.
Well, I'll just very quickly say that when you choose a target, you've got basically either a metallic or a compound target, and the energy of your surface binding energy is going to impact the kind of distribution of your kinetic energy of your atoms as well as the ionization, and that kind of has implications for your film formation. But I'll finish it there and move on.
Hello, everyone. Can you hear me?
Yes, yes.
Yes, okay. Pedro Vidal Fuentes from IREC. I'm gonna show you a little bit about material growth by sputtering. And well, we use sputtering for control the position of metals and oxides at IREC, and as a suitable and industrializable technique to grow them. Okay, next. So first of all, the nucleation will define how the film will grow in your substrate, and this will be defined by the thermodynamic conditions of the deposition or the deposit, and towards everything together with the reduction of the surface, the final surface energy. Also, a lot of things can happen or are happening when the atoms arrive to the substrate. So the atoms arise depending on the energy, the velocity, or when they hit the substrate, they can be re-evaporated. You can see it in the right bottom part of the slide. They can create metastable clusters, critical coalesce together to form bigger clusters, and directly get attached to the film. But this, as I said before, will be defined by the thermodynamical conditions. So if you focus on the bottom left scheme, you can see how, depending on the what's more favorably for the atom, if you see the red atom, if it's more favorable to attach to the kink, you will have some kind of grow. If it's more favorable for it to attach to a previous added atom to the surface, you will have a different kind of growth. So if you have, if it's more favorable for the impinging atom to grow in a kink, for example, you will have what's called a layer by layer growth of the substrate. So layers will start to fill ideally monoatomically in the surface, and when the layer is completed, you will start growing the next layer. Another way is that the atom prefers, or is more energetically preferable, to grow on top of a previous absorbed atom, and then you will have some kind of island growth. This island will expand with more atoms until they coalesce and they form a film. And then finally, you can have a mixture in which there is not a preferential reduction in energy of the two previous models, and you can have a combination of both. Okay, next. This will define what's called some structures on models, in which you can categorize how the films grow in the substrate. This is more or less independent of the materials. Of course, the values at which this happen will change, but you can define some parameters or that will modify the thermodynamic conditions of the film when it's growing inside the chamber, such as the substrate temperature in relation with the melting point of the target, the pressure of the chamber, the bias voltage between the cathode and the anode, the amount of ions versus atoms that are moving towards the substrate. And with this, you can define like zone diagrams in which, for example, there is a beautiful image in the right. You can see as you increase the substrate temperature, you start to have different growth mechanisms in your film, like moving of the. If you give, for example, a lot of temperature or enough temperature, you can make the interfaces between the growing grains to move. But if you give not enough temperature, this you don't have enough energy for the grain boundaries to move, so they will stay static, and you have more like filament growth, like in the second image from the bottom. Okay, so you can explore this for your materials when you are growing it, playing with the different parameters, knowing that they are all of them are more or less correlated to go to the final to the same destination process. Next, please. So for example, here are some examples of our molybdenum layers that will grow on glass. And you can see that increasing the argon flow, we arrive from a more or less not somehow amorphous film to a bit crystallized film. And we have the same effect if we increase the bias voltage in the substrate. So you can play with all of these conditions together to arrive to the final point. Next. This is another example more to illustrate the island versus layer by layer growth. So we have in this both, we are trying to operate a stack of tin, copper, and zinc. And by modifying the tin conditions, you can see how we can move from an island grow, that is the central image, and the EDX image on the left. You can see the thing is following an island grow, and it affects the upper layers. Modifying some growth parameters of this layer, you can arrive to have more or less a flat-like growth of all the layers. So next.
More.
Yeah, next, please.
I'm sorry, and again, it's
okay.
Okay. Okay, I don't know.
Okay, everything that I told is more or less ideal cases, aside from the examples, but the reality is that you can have a lot of separated effects, that reaction with the substrate is if it's not inert enough, nucleation spots to contaminate a contaminated substrate, intermixing of species. If you have, in the previous slide that I showed you, you have finally you have alliations between the copper, the tin, the zinc on the final film. You could have unstable targets if you have alloy targets, not enough vacuum, so you have oxygen incorporation, oxidation due to this present oxygen, and also strong effects of the crystal orientation of the substrate if it's not amorphous. You have, depending on the ending cut, the ending plane of your substrate, you will have a preferential orientation in the final film that you are trying to deposit. Okay, that's it. Thank you so much.
Thank you. So next is Ikram.
Hello, everyone. Do you hear me?
Not much, actually. Can you increase the volume?
Now it's okay.
Better, yes.
Better.
Okay, thank you so much. So, good afternoon, everyone. I will present overview about DC magnetron sputtering. So the first question that comes to our mind, what is the sputtering and how does it work? So DC sputtering or direct current sputtering is a physical, no, the previous slide, please.
Sorry.
So the direct current sputtering is a physical vapor deposition technique that uses a direct current as a power source. So during this technique, this technique used ionized gas molecule to vaporize the molecules of the target materials into the plasma. So next slide, please. So how does it work? So like any type of sputtering deposition technique, DC magnetron sputtering requires a vacuum chamber. It's also required DC power, positively charged sputtering gas atoms, and target materials and substrates. So as you can see from the scheme, so this is the process DC magnetron sputtering system used to deposit metal coating materials onto substrate. Can you press, please, because there is animation there. So firstly, the chamber fills with the insert process or gas ions, such as argon ions, and then the system applies a DC voltage to the target surface. And then the target coating materials became the cathode and the substrate became the anode. So then the neutral argon atoms became ionized when they collide with the negatively charged before this slide, before the previous slide. I think there is a problem in the animation. Sorry, because I did the animation to explain that, but I will try to explain that. So neutral argon atoms became ionized when they collide with the negatively charged targets and then eject into the high density plasma, which is generated through neutralization. So the positive ions condense and then form the thin film on the substrate. And the magnetic field traps electron over the sputtering target, preventing ions bombardment and increasing the deposition. Sorry, there is a problem in this scheme because there is animation to explain that. So
Yes.
what is the role of the magnetic field in the magnesium sputtering? So a magnetic field is used to confine the electron close to the, one more click please, confine the electron close to the target, which is to improve the ionization, for the low pressure. So this increase the plasma density and allows sputtering and low pressure and voltage. Yes, Editha, one more time.
Then, yes.
Yes, move to next slide.
Recording in progress.
Again? No.
Yeah, again, one more time.
Okay, so.
So here are some examples of conductive materials deposited by DC magnetron sputtering. So firstly, we have one click, please. There is animation. We have conductive materials like, yes, one more. One more. So we have, for example, we have transparent conductive oxide like TCOs. We have FTO, for example, ITO. Silver, gold, etc. And we have conductive coating like, for example, titanium netherite. And for non-conductive materials cannot be deposited by DC magnetron sputtering, since the non-conductive materials on the substrate prevent the electron flow through the anode, which is target. Next slide, please. So in this, one more time. So this slide present or show summary difference between RF and DC magnetron sputtering. So this is a short comparison. So you can see, for example, if we compare DC with the RF sputtering, in point of view, cost and complexity, we're gonna find the best is DC magnetron sputtering. But for RF, for example, is expensive and complex than DC sputtering. And for sputter rate, we have 100% of DC for DC sputtering, and RF sputtering, for example, 20% of DC and no magnetron. And for maybe you will understand more about the RF sputtering with the next speaker, and then the next speaker can explain more about that. That's it. If you have any question, you are welcome. And thank you for your attention.
Thank you, Ikram. Sajef?
Could you hear me?
Yes.
Okay. Hi, everyone. I'm Sajish. I'm PhD student from Tallinn University of Technology, and I will be giving some talks about the radio frequency sputtering. Could you go to the second one? Okay, so what is radio frequency sputtering? As you can see on the left side, I have the schematic diagram. And it's like simply, as our previous presenter said, like we have like the, based on the power supply we are using for the sputtering, it have like different kind of sputterings. So in this case, we are using an alternating power supply, which will have like a frequency in the radio frequency range. And if you check the components in that, you can see like chamber, sputtering gas, target and substrate. These are same compared to the other sputtering techniques. But here we have two more new parts, which is like the RF power supply for sure, and then the matching circuit. I will be explaining about these two more detail. And what's happening here is like due to the change in frequency, like in the DC sputtering, the target was like negatively biased, but in the RF sputtering, since it's an alternating power supply, the polarity of the target will be changing up and down, and this will help us to like avoid any accumulation of charges. Like in the case of DC, like since it's like always negatively biased, there is a chance that there will be like more positively charged ions will accumulate over there, and it will disrupt our sputtering deposition. So that can be avoided since like our polarity is changing, and this method is much easier for the deposition of the insulation materials also. So could you go to the next one? So why, like if you check like most of the RF sputtering machines, you can see like internationally most of them are using 13.56 megahertz frequency. So why it is, like I was looking on to that. So I then find out like, okay, then it has much more importance. Like if it is like less than 40 kilohertz frequency, then the electrons and the ions will be able to follow these changes. Like we need only the argon ions to hit the target and then make the sputtering happen. But if it's like less than 40 kilohertz, then it will be able to follow that polarity. But if it's more than that, it will be always focused onto the target, and we will get much more sputtering from the targets. And that's why, and also they have some regulations, and they thought like to make this 13.56 megahertz to be like a standard one for everything. And it's also like helps us to remove is the appropriate frequency to remove all the to avoid this accumulation of charges on this charged material. So could you go to the next one? So yeah, this is like our second main part, which is this matching circuit. So you can see on this schematic diagram, you will see the RF power supply, and then there will be like a matching circuit. So why we are using this matching circuit? It is like this RF power supply. It will generate the power, and the thing is like it should be completely transferred to the load, which is like our magnetron. So if it is not like completely transferring, it is not so good. Like in case like if the impedance of this power supply as well as the impedance of the magnetron is not matching, it will be like reflecting back. That's the main term used in the RF sputtering. They will be like if the all time power is not transferred there, it is called reflected power. So if there is like high reflected power coming back, it will be very bad for our power supplies. So that's why like that's the main job of this matching circuit. It is like adjusting the impedance between the power supply as well as the magnetron sputtering. So what is inside is like in the matching circuit, there is like variable inductance and capacitance. So you will be able to change this inductance and capacitance. You will be able to match this impedance. That's the main job, what happening in the matching circuit. And you can see one of the sputtering power supply, RF power supply, and the matching circuit that I used. It was supplied by CERN from USA, I think. And it is like you can see the parameters inside. You can see this 120 watt, which is the power that I have given, and you can see it's not so clear on there. There is REF, which means like reflected power supply. It's showing like is it matching, and if it is like 2, it should be 0 for an ideal power conversion, power transfer. And on the right side, you will see the matching circuit parameters, load and tune, which indicates this inductance and capacitance, so that it will we can tune it and then make the reflected power supply to zero. So could you go to the next one? So yeah, as all have like good and bad, so we have the benefits and limitations for the RF power supply, our RF sputtering. So the good thing is like obviously the deposition of insulating materials. You can easily deposit insulating materials with this method. It will be very difficult in the DC sputtering. And personally, I was depositing zinc oxide and aluminum oxide in this case, and I was also depositing doped zinc oxides also. And it have low substrate heating, and you can work on this low argon pressure compared to the DC sputtering. And it's much more stable process in the DC sputtering. If you have like there is a term called arcing, which is like if you have not like uniform sputtering, and this will affect the target also. So it is much more less in the RF sputtering, and as well as I said in the previous also, you can avoid this accumulation of these charges. And there is also a limitation, of course. It's like very low rate of deposition compared to the DC sputtering in the and you can see this much more complex system because you have this matching circuit and comparison, and you have to do all these things. And of course, this price is like the RF power supply, and along with the matching circuit, it will be much more costly for this machine. So yeah, that's all from my part. I think you enjoyed. Thank you.
Thank you. Thank you.
Excellent. Thank you to the first 5 speakers. I would suggest we have a little 10-minute break. So maybe coming back in, at 10 to 2, if people want to go get a coffee or a tea or stretch your legs or whatever, and come back. Does that sound all right?
Thank you. So we can have stop.